Okay, this video is for the solutions for momentum problems number 4 that you got off of Schoology. And hopefully you downloaded this, tried these problems already, and are now watching the video so you can see if you got them right. And if you couldn't get them right after you tried, then you watch this video for the step-by-step breakdown of how to solve these problems. So I have the 3 basic guidelines for when you want to solve a collision problem where the objects are going to stick together and you're going to have an inelastic collision because you're going to lose kinetic energy. And no momentum is going to be lost in this collision to heat or sound. So all the momentum is going to be conserved. So all that's basically saying is the momentum of the train cars before the collision has to be equal to the momentum of the train cars after the collision. So when these collide, the total momentum is going to be the same. And since the trains are going to be connected after they collide, we're going to need the total mass of both trains combined so we can solve for what the velocity is going to be. So we know that the formula for momentum is P equals mv. And if you haven't been in one of my classes, you'll know that P is the symbol for momentum because back in Newton's day, the term they used to describe the impetus, well, they called it impetus, this quantity of motion they called impetus. And I was already used for imaginary numbers, like the square root of -1. And M is already used for mass, so P was the next letter down. So P became the symbol for momentum. So momentum is mass times velocity. And if you rearrange that formula to solve for velocity, you get momentum divided by mass. So if all the momentum's conserved after they combine, if we just get the total mass, divide that into the total momentum, we should get the speed of the cars after they've collided. So first problem was really simple because train number 1 is not moving. So its momentum is 0 kilogram meters per second. And we want our units to be in SI units for momentum. So we're always going to put things in kilograms, meters, and seconds. And train 2 is going 4 meters per second to the left and has a mass of 5,500 kilograms. So the momentum of this train, 5,500 times 4, is 22,000 kilogram meters per second. Sorry if my hand's covering that up, I am a lefty. Now, the total momentum after the collision is going to be the momentum of the 2, and this one's 0, so it's just 22,000 kilogram meters per second. We put a dot there because it's a multiplication problem. And we're going to divide that because we said in our formula here, the velocity is the momentum divided by the mass, the total mass of both cars. So the total mass of both cars are 4,500 and 5,500. So that's 10,000 kilograms. And now we can do our math. Kilograms divided by kilograms is 1, so they cancel out. Cancel that out, cancel that out, cancel that out. Now we're left with just meters per second, and we have 22 divided by 10. That's 2.2 meters per second. And so we're going to write that down here. 2.2 meters per second to the left. Because momentum is a vector, so it has to have a magnitude and a direction. So that was the first problem. We set that one up to be kind of easy just to go through a momentum problem to get you guys in the habit of saying total momentum before and after the collision is the same. So there's the total momentum after the collision, there's the total mass, and we use that to solve for the velocity. Now let's go on to problem number 2. Okay, for problem number 2, we have Thomas the Tank Engine moving to the right down the track at a speed of 2 meters per second. James is on the same track behind Thomas, but is moving 6 meters per second. If Thomas has a mass of 2,000 kilograms and James has a mass of 1,500 kilograms, what will their velocity be after they collide and stick together? Now, again, we're going to assume there is no outside forces, no momentum is going to be transferred to heat or sound, so no momentum is going to be lost. So what we want to do is get the momentum of both trains, add them together because they're going in the same direction, and then divide that by the mass of both trains because they're going to be coupled together and moving as one. So Thomas is 2 meters per second and he's 2,000 kilograms. So that's already an SI. So we're good to go with that one. So that is 4,000 kilogram meters per second. And James is 1,500 kilograms at 6 meters per second. So that's 9,000. We multiply that. 9,000 kilogram meters per second. And as we said, they're in the same direction. So when they collide, we add their momentums together and we get 13,000 kilogram meters per second. Now we want to divide that by the mass of both trains. So we're going to put that there. And underneath, we're going to get 1,500 kilograms plus 2,000 kilograms because that's the mass of the two trains. So that's 3,500 kilograms. So kilograms is going to cancel out and we're left with meters per second. And we have the zeros cancel out. So we have 130 divided by 35. So that is going to be around 3. So let's grab a calculator. So 130 divided by 35 equals, see, we've got 3.714. Now, in reality, we're going to go with just 3.7. I'm going to write it over here out of the way. 3.7 meters per second. And the reason we're just going to go to 3.7 and not all these other numbers is the number of significant digits we have in our problem here. We have 4 there, we have 4 there, but we only have 2 here, and we only have 2 here. So we only have 2 significant digits in our speeds. So our answer is going to reflect that we only have 2 significant digits. And this is going to be to the right. So we got the momentum of both cars, added them together because they were going in the same direction when they collided, divided it by the mass of both cars, and that's the speed they'll go at. And that kind of makes sense. James is going 6 meters per second, hits a much slower Thomas, who's heavier. So James has to speed him up. And in order to make him go faster, he has to go slower because the momentum is conserved. All right, next one. All right, problem 3, I went into full-on mean teacher mode. We've got a train moving from left to right on the track that has a metric weight, or what we call force sometimes, of 9,800 newtons. If that train goes 4,500 centimeters every quarter of a minute, and it collides with another train that only has 500 kilograms in mass and is moving 1 meter per second in the opposite direction, what's the final velocity? These trains are going to connect, of course, as we said in the directions, and they are going to stick together and they're going to move as one. So how do we do this? Well, we know that we need to find momentum, right? Momentum is mass times velocity, but we don't know the mass of the train. But we do know the force of the train. And if we use Newton's second law is force equals mass times acceleration. So we can figure out what the mass is because we know what the force is. The train is 9,800 newtons. And we know that the acceleration is, for gravity, 9.8 meters per second squared. So we just need to rearrange this to solve for mass. So if we divide both sides by 9.8, we end up with mass equals force, which is 9,800. Now I'm going to do something a little different here. I'm not going to write newtons. I'm going to write what a newton is made up of. A newton is a kilogram meter per second squared. That's what F equals ma says. Mass in kilograms times acceleration, which in SI is the meter per second squared, gives you a newton. So inside a newton, we have this inside of it, kilogram meters per second squared. And we're going to divide that by gravity, 9.8 meters per second squared. And the meters per second squared are going to cancel out, and we're going to be left with mass. And oh, the teacher's not super mean. He made this very easy to do. 9,800 divided by 9.8 is 1,000 kilograms. So if the train has a mass or a force of 9,800 newtons, then it has a mass of 1,000 kilograms. So now we got the mass for this train. So mass is 1,000 kilograms times, we're going to multiply that by, oh look, it's in centimeters. So we need to have that in meters because we want that in our SI units for momentum. So 4,500 centimeters is 45 meters. Or yeah, 45 meters every quarter of a minute, 15 seconds. Oh, look, we got meters per second now. And 45 divided by 15 is 3. So that momentum is going to be 3,000 kilogram meters per second to the right. All right, that's the momentum of train 1. Now, train 2 is 500 kilograms, and it's going 1 meter per second in the opposite direction. So 500 times 1 is 500. So you've got train 2 is going to have a momentum of 500 kilogram meters per second to the left. So when we combine momentums that are in opposite directions, we just subtract them, and then the net momentum is going to be in the direction of the greater momentum, which is going to be to the right, because this one's bigger. So we're going to get 2,500 kilogram meters per second to the right, and we want to divide that by the total by the total mass of both trains, and that'll be in kilograms. And that will cancel the kilograms out, and we'll be left with our velocity. And so the total mass is 1,500. So it's going to be 1,500 kilograms. So that cancels out, that cancels out, that cancels out. So you end up with 25 divided by 15. And you can put that in your calculator, and you'll get 1.666666 repeating. But we can look back in our problem, 2 significant digits, 4 significant digits, or 5 significant digits, 4 significant, so 2 significant digits is our smallest amount. Even within our problem here, 45 meters, that's 2, 15 seconds, that's 2 significant digits. So we're gonna round this off to 1.7 meters per second, because that's what's left. And that was to the right. So one train's going to the right, it's heavier and going faster. The other train is going to the left, it's lighter and going slower. So it's gonna slow this train down, and they're gonna travel together. And the smaller train is gonna get stopped and sent back the other way. So it's gonna be much worse for the smaller train. But that is how you get your velocities from your momentum problems like that. Even if your teacher is mean and won't give you masses outright, you can still figure it out by substituting it. By the way, one last thing about this problem, just to go back to the beginning again, real quick. I did this as like 3 separate problems. I did a Newton's second law problem to figure out what the mass was. Then we did a velocity problem to figure out what the velocity was, distance over time and all that. If you wanted to, if you're one of these students that has had algebra and likes to do substitution method, you could have actually written like, okay, momentum for train 1 is going to be mass times velocity. And we don't know what the mass is, so we'll substitute in the Newton's second law formula in there that will then solve for mass. So mass was force divided by acceleration times velocity, which it didn't tell us what the velocity was, but it gave us a distance and a time. So we can convert those into SI very quickly, and you would get, so momentum is force divided by acceleration times distance divided by time. That's the velocity formula for speed, and you would end up with momentum equals 9,800 newtons divided by 9.8 meters per second squared. And of course, when you divide those out, as we said earlier, you end up with a kilogram. And we want to multiply that by 45 meters divided by 15 seconds. And if we do that and multiply that out, you would get 9,800 times 45, which will give you 441,000 Newton meters over 9.8 times 15, which would give you 147 meters per second. And you would get 441 divided by 147. You get 3,000 and you'd have kilogram meters per second squared, so that would cancel one of those out, and that meter would cancel that out, and you would have kilogram meters per second. And that would be the momentum of that train. To the right, like we said. Hope that helps.